What's up, amigos? In this video, we'll be covering what the drag coefficient is. So we'll be looking at what is drag, what is the drag coefficient, which comes from drag, and why do we use the drag coefficient, and some examples. So first of all, what is drag? In aerodynamics, let's say we have an object of it could be any shape, and we have the free stream flow coming in at u infinity. This could be 5 meters per second, 1 meter per second, whatever. This free stream velocity, this flow is impacting this object. In this case, it will be a cube. And the flow will go over it and it will separate and create some sort of wake. And this is going to be a lot of drag. So this will, let's say, create a force on the object pushing backwards of 100 newtons. This force pushing the object backwards is trying to make the object stop. So if you throw this object, that's the same as if you were to have a free stream flow just hitting it. Either way, there will be a resistive force pushing the object back, and this is drag. This 100 newtons is drag here. And every object will have some type of drag, or some amount, whether that's 1 newton up to 1 billion newtons or whatever, just depends on the object itself, and we'll get into how we can calculate this. So why do we use the drag coefficient? What is it? So let's say we have another object now. We have a cylinder, or a sphere, sorry. And we have the exact same flow coming in, and it's hitting this object, and now it's creating also another wake of some description. And we want to compare these two objects. So let's say this cylinder as well, this sphere, is also producing a drag of 100 newtons. So does that mean that both of these shapes are just as good as each other or just as bad as each other in terms of drag production? The answer is actually no, because the force that is being produced, the drag, actually depends on several factors. The first one is the velocity of the free stream. So if, let's say, this was 5 meters per second, but this one was 1 meter per second, obviously they are different, so they're going to produce different amounts of forces. So an example of this is if you were to go outside on 2 different days, and there are 2 different wind speeds, you obviously feel more force on one day than the other. So we can tell that the drag depends on the velocity of the free stream flow, u or v. But that's not all. We also know that if we have a bigger object, that there's going to be more force on that object as well. So if we have a cube, which is 3 times as big, we're going to have a lot more force on there. So we know that there's some sort of length scale or area that this is dependent on as well. So what else do we know? Well, the third parameter that this is dependent on is something that we don't really understand, or we don't really understand intuitively because we don't experience it in real life. And there's the density of air. So if we have different liquids or different gases, they have different densities and they will change the amount of force. So an example of this is if you were to throw a ball in air, that's going to have a certain amount of drag associated with it, a certain amount of resistive force. If you get the exact same ball and you throw it in water, it's going to be a lot draggier. It's going to have a lot more force. So there's also the density component, rho, of the fluid. So the drag is not independent. It means that we can't really compare 2 objects and say, okay, this object is better than this object because it produces less drag in terms of its geometry. So that's why we come up with something called the drag coefficient. The drag coefficient allows us to compare 2 different objects to see which one is more efficient. So what is the drag coefficient? So the drag itself is a force, it's in newtons, and it's equal to half times the density times the velocity squared times some sort of reference area times the drag coefficient, CD. And this value here is very important. This is what we're after. So let's look at this and understand what this is. So the density is kilograms per meter cubed. The velocity is meters per second, and that's squared. So we can square both of these terms. S is the reference area. So in most situations, it is the frontal area. So if you were to take a cross section here, or through either object, and then you calculate what this area is of that corresponds to this object, that's the area now. That's the reference area. And this is meters squared, obviously. Now the drag coefficient is a coefficient. It's non-dimensional. It has no units, no dimensions. And the reason why this is important is because now we can compare 2 different objects. So the drag is a force, and we know that force equals ma from Newton, and that equals kilograms per meter seconds squared. So if we put this on this side, kilograms, meters per second squared, these units will cancel out, and what we'll be left with is kilograms, meters per second squared, kilograms, meters per second squared. So this term, the units of this term, is equal to all these units. So if we were to bring all this on the other side, we have drag divided by half rho v squared times s equals CD. What this means is the force, the resistive force, newtons, divided by half times the density of the liquid or gas that we are in, times the velocity that this is traveling at, squared, times this area, equals the drag coefficient. So what this allows us to do now is calculate what the drag coefficient of each of these objects are, each of them is, and then we can see which one is more draggy than the other, which one is more efficient, which one is less efficient. So in this particular case, the cube, the drag coefficient of a cube is actually 1.05. The drag coefficient of the sphere is 0.47. From here, we can tell immediately that the sphere is more efficient in terms of its travel, because it's not going to be producing nearly as much drag as the cube, because the cube has more than double the drag coefficient if we put it into this equation, regardless of if we have the exact same density, the exact same velocity, and the exact same reference area, so the exact same units here and terms, the drag will be greater for the cube because the drag coefficient is greater. So why do we use this? The drag coefficient is very important for everything because it allows us to compare objects. So if we were to have a cube and we want to modify it slightly, let's say we want to make these corners more chamfered or rounded. So now we can test that object and we can see what the drag coefficient will come out to be. We can then objectively determine whether that is an improvement or not. So if we were to do that and we found that the drag coefficient now dropped to, let's say, this new cube, the cube Neo is now 0.9, we can say that there's a drag coefficient drop, and this is a beneficial modification. On the other hand, if it goes up, then we can say, no, it's a bad modification and we don't want to do that. So I've given you a couple of examples here of some different drag coefficients. We know that the drag coefficient of a cube is 1.05. The drag coefficient of the sphere is 0.47. What about some other real-life objects? Well, a Boeing 747, the drag coefficient of one of these, an entire airplane, is 0.31. So it's actually very good considering how complex it is. So compared to a simple shape, something like this or this, the Boeing 747 has wings, it has a tail, it has a fuselage, it has even landing gear, however that gets popped up into the fuselage. The drag coefficient is so low. However, a Boeing 787, which is a newer airplane, has a drag coefficient of 0.024. Sorry, there should be a 0 in here. I should put one there. 0.024, so it's even better. That means that the 787 is a massive improvement. It's an improvement of 0.007. And one final thing that I want to mention is another way of describing drag coefficients. So right here we have all these coefficients here. We can also use a industry term called counts. So a count, let me move this up so you can see it a bit better. A count is thousands of drag coefficients. So if we have a drag coefficient of 0.024, this equals 24 counts. So we can say, okay, this modification reduced the drag by 3 counts. That means that it goes to 21 counts now. If we have a drag coefficient of 1.05, that equals 1,050 counts of drag. And this unit is not just reserved for drag, it can also be used for lift and other coefficients, but it's very common for drag in certain industries. So as a recap, let's go through what we just covered here. We talked about what drag is, and this is a resistive force. This is a force that is produced from flow hitting an object, whether that means that the flow is moving towards the object and the object is stationary, or the object is moving and in still air, or both are moving. So you can have a wind plus you throw a ball. Either way, there's some sort of relative motion between these two, and that produces a resistive force. The drag coefficient comes to this equation here. Drag equals half times the density times the velocity squared times the reference area times the drag coefficient. So we can rearrange this equation to get the drag coefficient here. And we use it so we can compare different objects. We can categorize quantitatively whether an object is efficient or not in its flight. So as a general rule of thumb, below a drag coefficient of about 0.5, so if the drag coefficient is below this or equal to it, then it's pretty good. If it's above 0.5, then it's fairly bad. And there are obviously some different levels there. And finally, some examples. We know that a cube is well documented that the drag coefficient is about 1.05. The drag coefficient of a sphere is 0.47. Interestingly, the drag coefficient of a Boeing 747 is only 0.031, so that's 31 counts. The drag coefficient of a Boeing 787 is 0.024, so that's only 24 counts. So that's the end of this video. I hope you liked it. If you did, make sure to like it and subscribe, and let us know if you have any other ideas of what you want us to explain here. If you want to look at fundamentals even more, like you're looking for a textbook or whatever to study fundamentals of aerodynamics even more, I recommend the textbook called Fundamentals of Aerodynamics by John D. Anderson. It's actually a textbook that I used back in my uni days, although I had an earlier edition. You can find the link in the description. And I'll see you in the next video. Peace out.